So I've invited the master of explaining complicated things in a very digestible manner. That is Shivam Gusai, who runs a consultancy called Decypher, where he offers decarbonization support to factories and also does a lot of thought leadership on really focusing on the solutions we can implement, getting them into factories and making sure that we hit our sectoral targets. So welcome, Shivam. Really great to have you here.
Thank you so much for the lovely introduction, Pauline. Yes, I'm really excited to be here.
Fantastic. So let's start. If you were doing an elevator pitch, so as short as you can, what are heat pumps? Why are they great? And maybe even better than some other alternative electrification technologies?
Yeah, absolutely. So quick elevator pitch for heat pumps. So of course, they're maybe one of the only technologies that gives you more heat than the electricity you put in. And of course, this sounds just magical and we're breaking all laws of thermodynamics for that matter. It's like, you can't just generate energy. But it's not from the perspective that all of the other ones start from, let's say, zero. Heat pump is the only one which uses residual heat or just low energy heat from other sources and then combines it with the electrical energy to give a higher output. So it's not magic. It is basically the summation of waste heat energy and electrical energy then converted into a higher source. And it can give you up to 3 or 4 units or even 5 units of heat for 1 unit of electricity input. So it's a significantly more efficient system than almost all the other technologies available. And hence, as for the pitch idea, it is one of the most efficient technologies that can be used. And it not only does it solve for your waste heat, which is being released into the environment otherwise. So it's a good circular economy principle in terms that it's using the waste heat and generating some more heat back, which can be used in the process. So that's great. But it also kind of reduces your reliance on, let's say, electrical energy as opposed to an electric boiler, because the unit is 1-to-1 in electric boilers. Here it's maybe 1:4 or 1:3. So you need less electrical energy for the same amount of heat output that you would get between electric. And we don't have so much renewable energy available as of now. So using heat pumps can also work with limited access to renewable energy as opposed to electric boilers for the same amount of heat produced.
So could you break it down maybe into, in layman's terms, but a bit more technical, what is actually the kind of mechanisms behind this magic?
So everyone owns a refrigerator, I guess. It's very similar to what a refrigerator does, but maybe kind of reverse. So a refrigerator takes the heat from let's say the food and the other things within your refrigerator and then throws it out into the environment. This one kind of does the opposite, takes the waste heat from the outside and then gives you a more heated source. So it works there is basically 4 steps. So the first one is evaporation, then there's compression, then there's condensation, and then there's expansion. So I go through all of them in a very simple manner. So evaporation, we all know the water gets evaporated and that's how we get rainfall. But in this, we have a magic liquid, as we say. It's a refrigerant liquid, which has a very low boiling point. So it doesn't require too much heat to evaporate. So what we do is we take this refrigerant liquid and it's put into an evaporator, and any low source of heat from waste heat from other places, even in just the heat pumps used in houses, is just even the atmospheric air has enough heat which can be used today. But for industries, of course, we would try to use a higher heat source, a higher temperature heat source, because our jump is much bigger. So we use this refrigerant liquid. It is an evaporator. It uses the heat, evaporates and becomes vapor. The next step is compression. Is where the all electrical energy and everything else is being turned into how the energy would come out the other way. So when we compress this vapor, which is basically gas, we're increasing the pressure. And as we increase pressure, the temperature increases as well. So now we have high temperature vapor inside this chamber. So now we took it at a lower temperature. After we pressurized it, the temperature went up. So now it's much warmer than it was before. Then we send it for condensation, which is we turn it back into a liquid. So when it goes to condensation, it releases the heat. So it goes from a high temperature gas to water or back into the liquid state. So it releases the heat, and we use that heat to heat up our water or to generate steam for our applications. So this is the part where the energy is released in a higher grade, because we took low temperature heat, turned it into high temperature, and then released it back. Let's say it's part of the water circuit that we have in the factory. So all of this heat is taken to heat up the water, and then you get high temperature boiling water or near boiling water coming out. So anywhere from 60 to 95 degrees is very ideal and can be done by heat pumps super efficiently. Of course, when we go to steam, the thing changes because we have a phase change from water to steam, which is a very energy intensive process. So in that cases, we do need to change the configuration a little bit. We have a different condensation process, different compressor, different refrigerant liquid as well, which can give out a more higher output. The last step is expansion. So we take this liquid that we have and then we reduce the pressure. And so we reduce the pressure and the temperature also comes down with it, and it's back to its original form, wherein it can start this process all over again. So now it's become cool and it can take some of the heat and then evaporate again. And so when it's evaporating, it goes back into the same process, and we can keep this cycle continuously going. And so this is how basically a heat pump works. It's 4 steps, all thermodynamically realistic and well studied. No laws are broken, and it works out perfectly well. And we get high temperature output from the other end.
If I had physics teachers like you in high school, maybe I would have done better. That was very clear. Thank you. And could you talk a bit, because you used the word refrigerants, and there's quite a lot of interest in the solution also from a cooling perspective, which we know with things like heat stress and the countries that, where we want to apply this technology, the cooling aspect is really important for climate adaptation. Could you go through where in the process does the cooling come, and how does that work, and why does that make it an even more compelling solution?
Absolutely, because as opposed to, let's say, electric boilers, coal, gas, wherein you have to give it a fuel source and then you basically burn it, and it's quite intensive for that matter, and of course it generates heat for the environment. So we have dyeing machines which are warm, and you have wastewater going out which is also warm. So all of this creates, and most of the heat is being dissipated from all of these sources into the atmosphere or into the air, because heat goes from hot to cold always. So the atmosphere is getting really intense and hot. But what this machine is doing is it basically takes all of this waste heat, which would have otherwise gone into the atmosphere, but into the machine, and uses it to regenerate hot water or hot steam. So it doesn't let much of the waste heat escape into the atmosphere. It makes use of it. So it adds on to the principle that when you have these machines in place, it takes away all the excess heat, which would have otherwise been wasted and caused heat stress for the workers. It makes use of it. And because it's making use of it, there's nothing to go out. So it becomes naturally cooler for everyone else because it's using all the excess heat. An electric boiler or a coal boiler or gas boiler, none of them can do this. Mm-hmm. Only a heat pump can have this extra effect. Of course, electric boilers also have the advanced effect that it's not causing so much emissions and everything else, which is causing a problematic environment for workers. But an extra heating aspect of, or cooling down aspect is only thing that only heat pumps can do, and no other technology does that.
Fantastic. Super interesting. And I think, a really important consideration when we think of not only mitigation, but also adaptation. So you've mentioned, or you've compared the technology quite a lot to boilers, and an electric boiler is less efficient, but it is more of a plug and play electrification technology, which heat pumps are not. So could you maybe explain why it's not plug and play and how it is a different kind of, you've explained why it's different, but from a factory perspective, what would this mean to implement, and how would that be different than just, replacing a boiler?
So all the other boilers use a heating source which they heat up, and they have a lot of water coming in, and they just basically boiled off into steam. And then steam is then carried through pipes into different areas within your factory, wherever you need it. Of course, in a heat pump, you need much more work to actually get the residual heat that you need for this magic process, because it has the electrical component, which electric boilers also have, but it requires the residual heat. So you need systems to bring back all of that heat from different sources in your factory back to this one source, because you just can't set up multiple heat pumps everywhere. That would just not be very efficient for the matter, and also quite expensive. So we want it to be much more centralized. And so we need to get all of this heat back. So first we need to, it's a lot of more piping work. We need to obviously have safety regulations and everything else, because the steam carrying pipes are obviously well regulated and we have these things. But if we want to secure it back and channel it back through the factory, we need to make sure that it's not affecting the environment and it's not going across pipes. The one big challenge is most factories have been retrofit way too many times. Mm-hmm. So we have the whole problem of patches over patches. We don't necessarily fix things. We try to do whatever we can. So it's quite difficult in a lot of factories to just put in new pipes and new equipment that doesn't necessarily fit the size of the one that was there before. So we have a boiler room design and we have specific space. So you can't just, let me just take out this coal boiler and let's say put in a heat pump. The size specifications are different. You need to understand there's architectural problems, of course, whatever the generation of the steam is. If it's too high pressure, high temperature steam, you need different conditions and other things. So we need a lot of rebuilding that needs to happen, which is something that people don't really want to do. They're very familiar with their previous setups. If you have to do this, either you set up a new zone wherein you create this heat pump, or you have to replace something, which most factories don't have the capability to do because it affects your processing capabilities. You might have to shut down for a few months, which no mill wants to do. So there's a lot of aspect of, do they have enough flexibility to make this change? Will the brands be aligned with them as to like, okay, we're going to reduce our production capacity to a certain level because we're going to need some space, and 2 of our boilers, let's say we have 4 boilers and 2 of them are going to be down while we're replacing. Would you still stay with us, let's say in 6 months? Big challenge. So they don't want to do, and of course, then we also have the element of you need to do a root cause analysis for where your heat sources are, waste heat sources. So additional studies need to be done. You need to find out which source is worth it to actually pull off. Mm-hmm. If it's, let's say you need, 60-degree heat coming in as a baseline, and some of your processes were running at 65 or 70, it would not necessarily make much sense if the source is far away, because in the transportation you will lose heat, and maybe what you get is maybe below 60. So it's not very ideal. So you can't really get every point source of heat that is in your factory. You need to find the most usable ones and then see which is not too far away, because you don't want to just keep setting up pipes and losing out, and then you have to pay additional money for insulation and a whole lot of things. So all of this takes a lot of time for the factory, which they, frankly, in this modern environment that we have with how factories are being run and the margins are low and they have so much pressure for new innovation and new materials and new trials and piloting and everything else. The benefit is once you have done this, it is easy to replicate from a theoretical perspective. Of course, every factory will have their own problems in terms of where it is, what needs to be put, what pipes need to come in. But it's not that difficult. It's a very engineering heavy problem. Yeah. And any problem that is engineering heavy can be solved with good engineering. But if a thing doesn't work, there's no solving it, because you just need to fix the whole thing in the first place. So it's, I think I would point it as more of a willingness thing. And of course, there needs to be additional, maybe let's say you have to, with your manpower or workforce, you need to maybe educate them a bit more to use this new machinery, because it's not a very standardized thing. It works on a different principle. You need to understand that there's a refrigerant liquid and what the efficiency factor will be in terms of what's your input heat versus what output heat you want. Do you want hot water? Do you want steam? So it's 2 different systems. You would not have one heat pump for both. Yeah. You'll have to idealize. So sometimes what mills can obviously do to maybe make this easier as a process is, if you think you have enough hot water requirement and not so much steam requirement, you try to double down on this. You try to reduce your steam requirement altogether so that you can shift your percentage share of hot water requirement versus steam requirement in favor of hot water.
We've seen some really interesting, case studies or ongoing projects where we've had factories apply for a grant, specifically for a hot water heat pump. And they actually did a lot of preparatory work to reduce or actually eliminate the steam that they need. And this is a cellulosics mill. So it's really interesting to see, that level of upfront work that is also time consuming and, requires a lot of effort, but really pays off, because then you can buy a much cheaper heat pump, because hot water heat pumps are much cheaper than steam generating. And, you can very easily then electrify those processes. But from your explanation on whether or not it's plug and play, there really is quite a lot of work that has to be done. And as you said, a third-party engineering firm would probably be helpful. But it does boil down to the business case, right? Are you going to be rewarded with more business? Is there going to be a financial incentive from a brand to ask you to do this? Because you will see savings at some point, but there's a tremendous amount of human effort and time and learning. And then, of course, the CapEx as well. More work needs to be done on not just saying we need to electrify, but actually making sure that that financial and technical support is there as well.
Absolutely.
And you've actually thought of a creative way to support funding these types of projects. So will you end the episode with another elevator pitch? And this is for your double dividend protocol for those of us who might not have heard about it yet, but very interesting and creative way to fund these CapEx heavy projects.
We have such credible solutions in the supply chain side of things with new dyeing technologies, new chemistry, heat pumps, electric boilers. We have dozens of solutions from dozens of different manufacturers. So you can choose any permutation combination and it still works out really well. And they've been validated. And we know we have as much data as we can ever have for these solutions. There's always this tug of war between the industry in terms of what should we prioritize. We have limited funds and limited resources. And let's say majority of the brands want to pursue, let's say, the material side of things, because that is something that sits within their control. But then we also have supply chain side of things, which are much more impactful, maybe even so exponentially more, not even maybe 1.5x or 2x more.
More impactful from a carbon perspective, you mean?
Yes. Yeah, more impactful from a carbon perspective and also from a reduction perspective. So we needed to find a balance of how we can satisfy what the brands want to do and what they have control over, but while also making it, as you said, a good business case for the supply chain side of things, which are usually longer ROI periods and not as favorable. Most suppliers are not necessarily sitting on millions of dollars. That would be great, but they're not. So when all of these upgrades come in with CapEx heavy upgrades like heat pumps, which are a few $1 million a piece, it is quite difficult, and it usually happens through debt financing. So suppliers will take out a loan and they'll have to pay it back, but the payback period is beyond 5 years usually because it's an expensive technology and the rate of interest is quite high. So even if the ROI of the technology was, let's say, 3 or 4 years, with the interest period, it goes to 5 or 6. Yeah. Makes it quite unfavorable for them because most suppliers don't have certainty that they're going to have continuous business for the next 7 years at the same pace or even growing for that matter. And if this heat pump can actually get them more business. And the other side is brands are pursuing next-gen materials or any innovative material or even just a better class of materials for that matter. And it usually comes with a premium, which they have to pay. What we could do in this model is the supplier needs cash and they usually go to the bank. But what we do is instead of that, they go to the brand and be like, okay, you cover the CapEx. So the ROI now moves from me back to you. But the benefit is because I have this decarbonized technology in my factory, which is significantly more efficient, I have operational savings because I need less energy and less electricity and less water and less other resources depending on the type of technology you've inputted. So that takes my production cost lower. What I could do with this cash is I will cover the premium for the fiber on your behalf. You get the best of both worlds because for your initial investment, you're getting much longer worth many years of fiber, which you would have otherwise paid for. The title of my article that I wrote about this whole model is Turning Efficiency into Affordability. So we make use of basic common logic that we make systems efficient, which save us money, and we use that money to chase things that are maybe a bit more expensive and something that we can't necessarily justify all the time. And this way, the brands get what they want, which is the newer materials, which they control for. The supply chain gets decarbonized. The industry is moving in the right direction. Everyone's happy.
Yep. And I think we should end it there with this model where everyone could be happy. And, it's really fascinating to think about these different levers together because I think so often they are thought about differently. We're always curious. You and I talk about this a lot. So we're always curious for, what other brands or suppliers are thinking about this because it could be a really great way to drive forward, things like heat pumps that we've spoken about today, while also moving forward on these other topics. And to your point, I really liked how you said, this then makes it a really low carbon garment because a low carbon garment isn't just about a material, it's how that material has been processed. So thank you so much for sharing your new ideas of how we can actually implement these technologies. And of course, your great physics teacher, really clear explanation of how the technology works and also the challenges and opportunities that it has for manufacturers. So thank you so much.
No, thank you so much for having me.